Well, let me tell you something that I think is one of the strangest facts in all of physics. Take an atom, any atom, cool it down, take away its heat, take away more, keep going, get it colder than outer space, colder than the darkest void between galaxies, colder than anything you have ever experienced or could ever experience. Get it to absolute zero, the coldest temperature that the laws of thermodynamics even allow. And that atom is still moving. It is still vibrating. Not because you failed to cool it enough, not because there is some tiny bit of warmth left over. It vibrates because the universe will not permit it to stop. Quantum mechanics has written a rule into the fabric of reality, and the rule says this: perfect stillness is forbidden. Silence is impossible. There is a minimum amount of motion, a floor beneath which nothing can drop, and it is not zero. Think about that. The universe has a hum, a restlessness built into every particle of matter that exists. And no amount of cooling, no technology, no cleverness will ever make it stop. Now, I want to tell you why. You see, you probably learned in school, or maybe you just absorbed it from the world around you, that temperature is about motion. Hot things move fast, cold things move slow, and at absolute zero, 0 Kelvin, everything stops. All vibration ceases, all motion ends. The atoms sit perfectly still, locked in place like tiny frozen statues. That is the classical picture, the one that comes from thermodynamics as it was understood in the 1800s. And it makes sense. It is a beautiful, clean, satisfying picture. Zero temperature, zero energy, zero motion. Simple. And it is wrong. No, no, no. Not a little wrong. Not approximately wrong. It is fundamentally wrong in a way that tells you something profound about the nature of reality. Let me tell you what actually happens. In the early 1900s, physicists were building a new theory, quantum mechanics. And one of the first things they did was solve a very simple problem: a particle on a spring. You see, atoms in a solid, in a crystal, they are not just sitting there loosely. They're connected to their neighbors by chemical bonds, and those bonds act like tiny springs. The atoms vibrate back and forth. So the simplest model of an atom in a crystal is what physicists call a harmonic oscillator, a ball on a spring. Classical physics says you can make that ball sit perfectly still. You remove all the energy and it stops. But when you solve the same problem using quantum mechanics, using the Schrödinger equation, something remarkable happens. The lowest energy the system can have is not zero. It is 1/2 h bar omega. That is 1/2 of the reduced Planck constant times the angular frequency of the oscillator. And that number, small as it is never zero. It cannot be removed. It cannot be extracted by any physical process. Physicists call it zero-point energy. Now, for a typical atom in a crystal lattice vibrating at around 10 to the 13th Hertz, which is a pretty standard frequency for these vibrations, that zero-point energy comes out to roughly 3 times 10 to the minus 21 joules per mode. That is tiny, unimaginably small by everyday standards. But it is not zero. And that is the whole point. It is the irreducible minimum, the quietest the universe can get. Now, why? Why can the energy not just be zero? Why can the atom not simply stop? And this is where it gets really interesting, because the answer comes from one of the deepest principles in all of quantum mechanics. You see, there was a physicist named Werner Heisenberg, and in 1927 he figured out something that changed our understanding of reality forever. He discovered that there are certain pairs of physical quantities that cannot both be known precisely at the same time. Position and momentum are one such pair. The more precisely you know where a particle is, the less precisely you can know how fast it is moving, and the reverse. This is not a limitation of your instruments. It is not about the clumsiness of measurement. It is a fundamental property of nature. The product of the uncertainty in position and the uncertainty in momentum must always be greater than or equal to h bar over 2. Now think about what this means for our atom at absolute zero. If the atom were perfectly still, its momentum would be exactly zero, no uncertainty at all. And if it is sitting in a crystal lattice, perfectly locked in place, its position would be exactly known too. Zero uncertainty in position, zero uncertainty in momentum. But Heisenberg's principle says that cannot happen. The universe does not allow it. So the atom does the only thing it can. It settles into the lowest energy state that satisfies the uncertainty relation. It vibrates with just enough motion, just enough jitter to keep the product of its uncertainties above that minimum threshold. That vibration is zero-point motion, and it is as fundamental as the uncertainty principle itself. Think about that for a second. The atom is not vibrating because something is pushing it. It is vibrating because the mathematics of reality requires it. Motion is woven into the structure of quantum mechanics at the deepest possible level. Now let me tell you about something practical, something you can actually see, that proves this is real and not just some theoretical curiosity. Helium. You know helium. It is the gas that makes balloons float. Light element, second on the periodic table. Now, you see, helium-4 has a very interesting property. It is light, which means its zero-point energy is relatively large compared to the strength of the forces holding its atoms together. Those interatomic forces in helium are extremely weak, van der Waals forces barely there. And the zero-point motion is so vigorous, so persistent, that it prevents the atoms from settling into a rigid crystal structure. What this means is extraordinary. Cool helium down to absolute zero under normal atmospheric pressure, and it will not solidify. It refuses. It remains a liquid, flowing, moving, sloshing around, all the way down to absolute zero. This is the only element in all of nature that does this. Every other element, you cool it enough, it freezes solid. Not helium. You have to squeeze it, apply at least 25 atmospheres of pressure to force helium into a solid state. The zero-point energy literally prevents it from freezing. Now compare that to diamond. Carbon atoms in diamond are bound together by incredibly stiff bonds. Very rigid lattice. The zero-point vibrational amplitude in diamond is about 0.04 angstroms. Tiny. The atoms barely wobble, but they do wobble. Or take lead. Heavy atoms, soft material, the zero-point amplitude is even smaller because the greater mass reduces the uncertainty-driven motion. But even lead, at absolute zero, vibrates. Every atom in the universe vibrates at absolute zero, no exceptions. Now, you might be wondering, well, has anyone actually gotten close to absolute zero? Can we test this? And the answer is yes, and the story is wonderful. You see, there is a law of thermodynamics, the third law, formulated by a fellow named Walter Nernst in 1906, and it says something very important. You cannot reach absolute zero in a finite number of steps. Every cooling process becomes less and less efficient as you approach zero. This is not just an engineering problem. It is not that we need better refrigerators. It is a fundamental law of nature. The universe has a floor, and you cannot touch it. But you can get close. Very, very close. In 2003, Wolfgang Kettle's group at MIT cooled a cloud of sodium gas to 500 picokelvin, that is 500 trillionths of a degree above absolute zero, half a billionth of a degree. That was the record for nearly 2 decades. And then, in 2021, a team at the University of Bremen in Germany did something remarkable. They took a cloud of about 100,000 rubidium atoms and dropped them down a 120-meter tower. Free fall. While the atoms were falling, they manipulated magnetic fields to create a Bose-Einstein condensate, a state of matter where all the atoms behave as a single quantum entity, and during that free fall, they achieved an effective temperature of 38 picokelvin, 38 trillionths of a degree above absolute zero. They published this in Physical Review Letters, and it is the coldest temperature ever recorded anywhere in the known universe. Colder than deep space, colder than the Boomerang Nebula, which at 1 Kelvin is the coldest natural place we know of. 38 picokelvin is unimaginably cold, and the atoms were still moving. Think about that. We built a tower, we dropped atoms in free fall, we manipulated quantum fields, we reached a temperature colder than anything nature has ever produced anywhere in the cosmos, and we still could not make those atoms sit still. Zero-point motion persisted, because it always does, because it must. Now, I want to tell you something even stranger, because so far we have been talking about atoms, about matter, about things you can at least imagine holding in your hand. But zero-point energy does not stop at atoms. It extends to something you might think has no energy at all: empty space. You see, in 1948, a Dutch physicist named Hendrik Casimir was thinking about the quantum nature of the electromagnetic field, and he made a prediction that sounded, well, a little crazy. He said that if you take two uncharged metal plates, just flat pieces of metal with no charge on them, and you put them very close together in a vacuum, in empty space with nothing between them, they would feel a force pulling them together. Not gravity, not static electricity, something else entirely, a force created by the vacuum itself. Now here's why. You see, quantum mechanics tells us that even empty space is not really empty. The electromagnetic field has zero-point energy too. Virtual photons, fluctuations in the field, popping in and out of existence everywhere, all the time. Between the two plates, only certain wavelengths of these fluctuations can fit, the ones that match the gap. Outside the plates, all wavelengths are allowed. So there are fewer fluctuations between the plates than outside them, less energy density inside than outside, and that imbalance pushes the plates together. This is the Casimir effect. And for almost 50 years, it was a theoretical prediction. Beautiful physics, but hard to measure. Then, in 1997, Stephen Lamoureux at Los Alamos National Laboratory measured it. He confirmed Casimir's prediction with remarkable precision. The vacuum of space pushes things around. Empty space is not empty. It seethes with zero-point fluctuations, and those fluctuations produce a real, measurable physical force. And you know what? Since then, the measurements have only gotten better. Ricardo Decca's group has measured the Casimir force at submicron separations with precision better than 1%, confirming the predictions of quantum electrodynamics. These are not vague theoretical ideas. This is measured, confirmed precision physics. The emptiest space we can create is still buzzing with energy. The quietest room the universe allows is not quiet. Now, let me tell you about something that connects all of this in a way I find very beautiful: phonons. You see, when atoms in a crystal vibrate, those vibrations do not just stay local. They propagate through the material as waves. And just as a wave of light can be thought of as a particle called a photon, a quantum of electromagnetic energy, a wave of vibration in a crystal can be thought of as a particle called a phonon. A quantum of sound. Phonons are not real particles the way electrons are. They are quasi-particles, collective excitations. But they carry energy, they carry momentum, they interact with other particles. And at absolute zero-point phonons still exist. The lattice still vibrates. Sound at the quantum level never fully stops. And different materials have different characteristic frequencies. Diamond, with its incredibly stiff carbon bonds, has optical phonon frequencies around 40 terahertz. Silicon vibrates at roughly 15 terahertz. Lead, heavy and soft, sits around 2 terahertz. Even at temperatures of a few millikelvin, these materials sustain zero-point phonon populations. The crystal lattice is humming, always. Now, here is something that seems like it should not work, but does, and it comes directly from this story about quantum vibrations and thermal noise. At room temperature, the atoms in a metal are vibrating wildly, thermally excited, bouncing around. Electrons trying to flow through the material keep scattering off these vibrating atoms. That scattering is what we call electrical resistance. The electrons cannot get through cleanly. They bounce, they lose energy, they generate heat. This is why your phone gets warm, why power lines lose energy over long distances. But cool a material down, way down, below a certain critical temperature, and something remarkable happens. The thermal vibrations drop, the noise quiets. And in that relative silence, quantum effects that were always there but hidden by thermal chaos suddenly become dominant. Electrons pair up into what physicists call Cooper pairs, bound together by an attraction mediated by phonons, by those quantum vibrations of the lattice. And these Cooper pairs form a kind of quantum condensate. They flow through the lattice without scattering, without resistance, zero resistance. This is superconductivity. You see, superconductivity is what happens when you quiet the thermal noise enough for quantum coherence to take over. It is the sound of atoms at their quantum minimum becoming the stage on which a new phenomenon can perform. And the field is advancing. In December 2024, researchers at SLAC and Stanford stabilized nickelate superconductors at room pressure for the first time, published in Nature. In January 2025, a team at Columbia University achieved superconductivity in twisted bilayer tungsten diselenide. And in December 2025, Max Planck researchers directly measured the superconducting gap in hydrogen sulfide under pressure, confirming theoretical predictions. Room temperature superconductivity at ambient pressure remains unachieved, but every year we get closer. Every year we understand more about how quantum vibrations shape the behavior of matter. Now let me step back and tell you what I think all of this really means. You see, people talk about energy as if it is a substance, a fluid you can pour, a stuff you can hold. But energy is not stuff. Energy is not a thing. Energy is a mathematical quantity that remains constant as a system changes. It is a property of motion, of configuration, of fields. And zero-point energy is perhaps the most fundamental expression of this idea. Even when nothing is happening, when temperature is zero, when every classical reason for motion has been removed, energy persists. Not because something is being added from outside, because motion is woven into the mathematics of reality at the deepest level. The world is a dynamic mess of jiggling things, if you look at it right. And this is not a small footnote in physics. This is not some obscure detail that only matters in laboratories. This touches everything. Put your hand on a table. Those atoms in the table, the atoms in your fingers, they are vibrating right now. Some of that vibration is thermal. You are warm, the table is warm, there's plenty of thermal energy sloshing around. But if you could somehow cool your hand and the table down to absolute zero, the atoms would still vibrate. You would still never truly touch perfect stillness. The electrons in those atoms would still have zero-point energy. The bonds between atoms would still hum with their irreducible quantum vibration. And think about the vacuum between galaxies. Millions of light years of apparently empty space. No matter, no radiation, nothing you could see or touch. And yet that vacuum is alive with zero-point fluctuations of the electromagnetic field. The Casimir Effect proves it. Two plates in a vacuum feel a force that should not exist if empty space were truly empty. Space itself vibrates. Now, there are things we do not understand about this. I should be honest about that. The total zero-point energy of all the quantum fields in the universe, if you add it all up naively, you get a number that is absurdly large, far larger than the observed energy density of the vacuum. This is the cosmological constant problem, and it is one of the deepest unsolved puzzles in all of physics. Nobody knows how to resolve it, not yet. We keep looking. That is science. And there is another question, maybe even more profound. Is zero-point energy, real energy, the kind that gravitates, that curves spacetime? Or is it a mathematical artifact that shows up in our equations but does not contribute to gravity the way other energy does? The Casimir effect says something is there. Gravity says, well, we are not sure. Nobody has a complete answer. The universe does not tell us, not yet. But here is what we do know. We know that at absolute zero, atoms vibrate. We know this is not thermal motion. We know it comes from the uncertainty principle, from the deepest structure of quantum mechanics. We know that helium refuses to freeze because of it. We know that the vacuum pushes metal plates together because of it. We know that superconductivity emerges when thermal noise drops low enough for these quantum vibrations to matter. We know that researchers in Bremen reached 38 picokelvin and the atoms kept moving. Let me tell you something. Our imagination is stretched to the utmost, not to imagine things which are not really there, but just to comprehend those things which are. And this, I think, is one of those things. The universe vibrates. Always. not because something makes it vibrate, but because vibration is what the universe is. Motion is not something that happens to matter. Motion is built into what matter means. Remember where we started. You cool an atom, you take away its heat. You get colder than space, colder than anything nature has ever produced, and the atom still moves. Not because you failed, because the universe has a rule. Perfect stillness is forbidden. There is a floor, and you cannot go below it. There is a hum, and you cannot silence it. Every atom in your body, every atom in every star, every fluctuation in the emptiest void between galaxies carries this irreducible vibration. Silence is not difficult. It is not merely impractical. Silence is impossible. The universe forbids it. And I think that is beautiful. Reality has a voice. It has always been speaking. And the most remarkable thing is that it can never, ever stop.